Bill has been a pioneer in promoting and fabricating FRP, or fiber-reinforced plastics, in architecture for decades now. And he's probably one of the most knowledgeable people in this field that I know. He has worked on many well-known architectural projects, including the San Francisco MoMA with no header, the Broad Museum with Dylan Scafidio, the SIAC Pavilion with Zaha Hadid, the Bing Concert Hall in Stanford, Bloom Lantern with Greg Lynn, and many, many projects with artists and architects from all over the world. Like many of the faculty here, Bill believes that the advancements in composites that has dominated aerospace and automotive and boat building industries for decades will and can be brought into architecture and revolutionize how we think about construction today. Collapsing skin and structure, pattern, texture all into a single lightweight component. Components that are limited in size only by the mode of transportation. Bill is and has been such an innovator in this field, and it's a real pleasure to have him here today to share some of his war stories and projects with our students. So without further ado, I'm very pleased to welcome Bill Kreysler to SIAC.
Thanks, Herwig. Thank you all for coming. I'm here to, just hit the space bar, right? I'm here to talk about the future, which is a little weird because I'm probably the oldest guy in the room. But what I thought I'd try to share with you today is the process of how one might get to where we've landed. And believe me, it's not a short path. It took a long time. But I thought I'd share with you some of the stories and some of the things that led up to the fact that we're now getting to work with some great projects and continuing to push the envelope into the future. So I found this video this morning, actually, and this is an example of how the future's made. This is a little video about the America's Cup boats. My background originally was in sailboats, building racing sailboats. And so I try to keep track of what's going on in that field, and I stumbled across this little video, and it kind of is an example of how a vision can be realized. No one's ever done what these guys are trying to do before. No one has ever built a sailboat that functions the way these things are supposed to function. And yet, they went ahead and they took a leap of faith, and they're basically creating the future. If they make this happen, it will have ramifications throughout the whole sport of sailing, but beyond that, perhaps even other things. And that's one of the ripple effects that happens when you sort of start exploring new ideas and new ways of thinking. So, here's an audio with this. Kind of funky at times. You just have to drones on a little bit here, but I'm going to jump ahead. So again, obviously a rendering, but still, this is the idea. So this is somebody's vision. This is why this is your job. figure out how
Southerly changes
So-
all the time.
I don't want to spend too much time on this, but I do think that it's interesting because at this point, like I said before, this thing has never happened. Well, there we go. I want to try to get to the next slide. Oh, here we go. Here we go. I got it. All right, so here's the problem in the construction. Whoops. Here's the problem in the construction business. That curve on the top is the productivity for industries other than the construction industry. The curve on the bottom, the blue curve, is the productivity curve for the construction industry. We're the only industry in the world that has actually become less productive since 1994, whereas everybody else is just taking advantage of all this new technology and utilizing it. So there's the opportunity right there. That's what you call low-hanging fruit. Thanks. Is that going to work better? And one way to get there, in my view, and I think in the view of others, is through the use of composite materials. Now, composite materials, the way I think about them, are fiber-reinforced polymers, or resins reinforced with fiber. And those fibers can be anything from hemp and jute and switchgrass and glass fiber and Kevlar, all the way up to carbon, and now there's even new fibers that are stronger than that. The reason those are efficient is because there's so little of it you need to use. Whenever we do a life cycle comparison between composite materials and conventional construction materials, it's remarkable how the so-called plastic, the material that everybody assumes is going to be very inefficient environmentally, turns out to be oftentimes, if not almost always, a better choice environmentally because it uses so little energy to make and it uses so little material to create a shape. So here's some of the other industries and what they've learned how to do with composites. That's a guy, that's a guy standing on that wind turbine blade, and the blades now I think are, I don't know, they're getting up to 80 meters long. They're unbelievably big, and they're all made out of composites. That's a single part. That is, as far as I'm concerned, a monocoque building waiting to happen. Because you take that thing and you make it a little bigger around, and you stand it up and you punch some holes in it, and now you've got a building without any structural steel, without any of the things that go along with a traditional building. And it's, it's just not out. In fact, Peter Testa figured that out 75 years ago. Was that about right? No, quite a while, with his high-rise out of carbon fiber. The marine industry virtually taken over by the composites industry. Transportation, the bullet train in Japan, but all over the world, composites. Obviously, sporting equipment, the pole vault, corrosion-resistant tanks. You can store chemicals in these tanks that you wouldn't dare put in a stainless steel tank. So this is an example of some of the things we've done. This is a building we did several years ago now, based in large part on composite materials and digital tools. And in those days, digital tools for us amounted to a 4-foot by 8-foot plywood CNC machine we made, because we didn't have any money, and we had to figure out a way to take advantage of this new idea. So we built one, and it worked. And we did a whole bunch of things with that little 4x8, 2-axis CNC machine. And I'll show you some more of those in a minute. This is a more recent project. This is Bing Concert Hall at Stanford. Those curved wall panels and that big ceiling is all FRP. This is the building in San Francisco, the Museum of Modern Art. There's 710 compound curved panels there. No two panels are the same shape. So every single panel on that building had its own female mold. And in this case, the reason we got this job wasn't necessarily because of the FRP, it's because we could make molds inexpensively enough that the architect could get what they wanted. And the other people that they were talking to were telling them, oh, you can't afford to make a mold for every part, that's ridiculous. This is a job we recently finished in Tulsa. This is an all-composite assembly of about 125 FRP panels. The interesting thing about this is that the panels bolt together, and there's no structure other than the FRP and the vertical column. So about every 20 feet, there's a vertical steel column, but everything in between it, all the support structure, built, by the way, for the local wind loads, which are pretty severe in Tulsa, and that's all FRP. They're all compound curves, they're all different shapes. There's no two panels the same. Just putting this thing together was no small task. But it's been a long haul, like I said, and to get where we are today, we started out with that. That's the CNC machine we built. It's plywood. It's got a little Bosch die grinder we bought at Orchard Supply Hardware, and it's got some parts and pieces we bought off the catalog and some servo motors we got from a company down the street from where we were. And with that, we started learning about digital fabrication and what you could and couldn't do with it. This is in probably 1987, 88. And one of the things we just got to thinking about was, well, if you just cut two-dimensional pieces and you stacked them up, you could create a three-dimensional shape. So this is a stack of 1-inch thick foam that was stacked up into the form of a letter, and it was for the East Bay Municipal Water District building, and it's been up there for, I guess now 40 years. There's the mold, all made out of 1-inch thick slices of foam cut on a 4-foot by 8-foot 2-axis CNC gantry. Then we thought, well, okay, we've got this CNC machine, we can create a shape. What if we added another axis to the cutting process by using a mechanical axis and build up a bunch of hexagons or polygons that we cut on the CNC machine. Well, actually we didn't, we cut it on a bandsaw with the jig. And then we put them all together on this armature, all mounted onto a steel table. And then down in the lower left-hand corner, you can see this little wheel, and that drives a rubber belt that drives a caster wheel that's rubbing on the underside of this disc. And we spin that around, and we created a fiberglass mold that built this sphere that's an 8-foot diameter sphere. That came out fine. And the way it was done was very much like this project, where there's a cupola we were doing for a fellow who was building a little chapel for his wife. So we thought, well, you know, it's a kind of a funny shape, but we've got this turntable and we've got this CNC machine. We could just take a cross-section of that curve and cut a piece of plywood out, like Don is kind of rigging up there. And along that plywood, we would slide a little tool that we made that had a piece of aluminum nailed on the edge of it, and it would start carving as the table spun around. He would just gradually slide that big curved piece of plywood in a little closer and a little closer until finally it cut the shape. We made a mold off of it, and we made these cupola steeples, or things, whatever you call them, roofs. All with a 2-axis CNC machine on a 4-foot by 8-foot platter. Then along came Klaus Oldenburg. This was also back in the late 80s, with this model of a necktie he was trying to get built in Germany. And the problem he was having was that he couldn't get anybody to make the patterns for the aluminum castings. And so he'd learned that we had this laser scanner, which in those days was pretty brand new stuff. We had bought ours used from some guy in Virginia, which later turned out to be the CIA. I never knew that until later. But we used it to scan this, and we could make the molds for him, for the foundry, or the patterns. But then we learned that, well, that's not quite the shape, because his engineers were telling him he couldn't make it that thin. He was going to have to make it thicker because there wasn't room inside to put the steel support structure. So by then, finite element analysis was beginning to become something you could do in a PC. And we said, well, maybe we can make the fiberglass the structure, forget about the steel inside. So he said, well, okay. And that's one of the nice things about working for artists. They're willing to sort of try things that you wouldn't be able to really try in a building because of codes and all that kind of stuff. So we did a little work on that, and we figured out, we could do it. We could make this all composite structure and get rid of the steel and keep the shape just the way the artist wanted it. So we then got out our 4x8 sheets of foam and our stack of our little CNC machine, and we started cutting out slices and numbering them, and we started putting them together. We sand the rough edges off by hand, and we fiberglassed over it, and we just kept going, sort of like on and on. Down the center of it, we had to lay up this big fiberglass beam, and there is a piece of steel there, but that only goes up about 3 feet, up just past the necktie. The rest of it is all composites. And there's the two halves being put together before they're fiberglassed. There's the two halves in the process of being fiberglassed. There it is in the first stages of finishing. There's the finish coat with the final touches of the finish being put on. And there's the sculpture in Germany. It came over to the job site in a single piece, which got all the way from Petaluma to Frankfurt. And the only thing is it couldn't get underneath this aqueduct thing, so they had to bring a crane in, and the job site was about 1/4 of a mile away. But this is the only place it couldn't go, so it had to go up over the top of that, down onto the same truck it was on, and then over to the job site, and then installed. And that's there in front of the DG Bank building in Frankfurt, or at least I think it is, was there last time I checked. Here again, 2-axis CNC machine, bunch of cross sections of plywood, molds for the Davies Symphony Hall, basically boat building technique, only using the assistance of a CNC machine to create a bunch of cross sections and curves and little notches where battens would go, so that we could then strip plank over the whole thing with thin pieces of door skin we bought at the Home Depot for $3 a sheet. And that's what the surface looks like. That's a compound curve mold. There it is with a coat of primer on it. There's the panel being made in it. The reason we got this job is kind of an interesting story. We were supposed to make the molds for this project, and they were to be made out of precast concrete because the acoustician wanted the panels to weigh 40 pounds a square foot for acoustics. Well, fiberglass's big claim to fame is it's lightweight. So why in the world would you make a fiberglass panel if it had to weigh 40 pounds a square foot? And the reason was that the building this was going in was already built. And the only way to lift the panels up was to rig off the trusses, but the trusses weren't strong enough to pick up an 10,000 pound panel. So we were sitting there listening to them, trying to figure out how to lift these panels up, and we said, well, they don't have to weigh 10,000 pounds when you install them. They just have to weigh 10,000 pounds when the music starts. So why don't we make them out of fiberglass? We'll make them hollow. We'll design and engineer them for the heavy weight. We'll mount them onto the structural support designed for the heavier weight. We'll pick them up with a little electric winch because they won't be very heavy. We'll put them on the side of the clamp, bolt them to the side of the building, and after they're installed, we'll come and fill them up with sand. So that's what we did. And there's like 57 tons of sand inside those panels at Davies Symphony Hall. And again, there's 88 panels. There's no two panels the same shape. There's 44 on one side. The other side are mirror images, but those are different molds. So those are 88 panels and one mold per panel. Then we thought, well, 3D, we're getting real sophisticated now. We're starting to scan things, and the software was getting to the point where it could do more than just slice it up. And Robert Graham wanted this sculpture done for San Jose. This is a wax model. It's about 8 inches. So we scanned it, and we decided we were going to get fancy. We were going to machine it out of a single block of foam. And so that meant we needed another machine. So we built this machine, those steel columns there. and a rotating table, because we learned how clever we were about rotating tables. And we put a cutting tool, which right there has a red cloth hanging on it so nobody bangs their head into it, on the end of that horizontal arm, and that horizontal arm went in and out, and it went up and down, and the table turned, so now we have a 3-axis machine. And all the drives on that were motorcycle chains and servo motors. And then we set up this block of foam. In those days, when you scanned something, you couldn't splice scans together, so you had to do one scan. So we tilted it at the angle that worked the best. We started machining, and we kept going until we had a foam model, and we sprayed gel coat all over it. We made a mold on top of the foam. We stiffened the mold all up. We dug the foam out of the inside. That was a scary moment because, you know, there's no going back at that point. And that's the female mold, all kind of held in place by being a little part of itself. Coated it with a black polymer concrete that included some obsidian that Robert brought up, smuggled in from Mexico, which he said was magic. I don't know if it was or not. And then cast the part at our dairy farm shop back in Petaluma and took it down to the job site, and it's there in San Jose today. Then along came Lawrence Argent with this 36-foot tall blue bear he wanted to do based on a little model that he had in his kid's toy chest, but he wanted to leave the triangles in, sort of like the polygons. And so he asked us if we could build this, and we needed a shop drawing, but how do you do a shop drawing of a blue bear? I mean, how do you do a drawing that shows the guys in the shop how this thing is supposed to go together? So we just made a little 3-foot tall version of him out of the same computer file. And from there we started cutting it up into pieces, making molds of those chips, putting them together, tinfoiling the foam to protect it from the resin. Otherwise it melts that resin. And then gel coating, that's the famous blue, which just happened to be the color that was in the 3D printer when he did it. But it turned out that he had to make up some story about why, when he presented this to his clients, and they said, well, why is it blue? And he didn't want to say, well, because I couldn't afford to change the color in the machine. So he said, well, there's a legend, an Indian legend, about a blue bear that comes up out of the Rockies every now and then. And they thought that was just fantastic. So they gave him the job right there on the spot. This was, at the time, the most complicated thing we did. There's our little shop drawing in the foreground, laying on the bench. And as it went together, we put a lot of the pieces together, but then we left these assembly joints, bolted to flange bolted assembly joints so we could ship it. There's one where the head bolts onto the body, and that's pretty tight. If you ever go to Denver at the convention center, you have a hard time finding these joints. That's all a residue of the tin foil, but that's the piece after it's been installed, and it was finished at the shop, so there was no work on the job site other than to assemble the pieces. This is a little story of the Stanford thing. I don't want to spend too much time on this stuff because I'm really anxious to give you guys some time to ask questions. So I forgot to say that you're going to be expected to participate in this discussion by asking me some intelligent questions. So I'm going to start with you. Okay? Okay? I will. If you raise your hand, I'll call on you, or I'll try to. This is a job that Ennead had at Stanford to build these acoustic wall panels, but it was a complex geometry, and they weren't quite sure how to do it. But the obvious choice, again, was concrete because of the density. The problem was the density of these wasn't 40 pounds. It was more like 20 pounds, 18 pounds and 20 pounds. And that was actually too light for concrete. You couldn't make a steel reinforced concrete precast panel that light. And the heavier it was, the stronger the support had to be in the building. So we got a call, asked if we could help, and we said, well, once again, we could make them out of fiberglass and then backfill them with concrete to bring them up to just the amount of weight you need, no more, and that way you're not spending more money on your support system, and plus, by the way, you'll get a nicer looking finish. So that's how that happened. This is the pattern for the ceiling panels. It had all these sort of wavy lines in it. This is the concrete poured onto the back and like an inch and a quarter thick. This is a panel being lifted to put on the truck. This is the mold for one of the side panels. This is about a 50-foot square mold. Again, just strips of door skins stapled down onto each other and then fiberglassed over with some primer. And that way we could make the wall panels in 8-foot wide pieces, which is small enough we could ship them and get them through the door, but we would know that they would always fit exactly next to the piece next to it. Because it was cantilevered off the building, and because although we love fiberglass, we don't get fanatical about it. When there's a time to use steel, we use steel. So this is the steel trusses we built to support the skin. And all of that came apart and was shipped to the job site in individual panels, which were then later assembled on site. And there's a panel being installed that was molded against the panel adjacent to it, then taken apart and brought to the site and being hung. And there's one all finished. There's the ceiling. The final color was put on afterwards. And one of the things we did that made it work kind of nice is you see that zigzag pattern in the center line. That was to avoid having a center line that looked like a center line, because the left and right side of this ceiling were symmetrical, so we didn't need to make a mold. We just needed to make sure that it didn't look like a molded part. So that zigzag kind of made it disappear when they put the paint on. So another project, this is another Lawrence Argent sculpture in Vail, Colorado. This is a bubble tree. It's translucent fiberglass bubbles, all with LED lights inside to change the lighting through a wireless control system. This was the most complicated, maybe the most complicated mold, certainly that we've ever done. I think the number of molds it took to do this was 350, I think, something like that. Steel, the bubbles are fiberglass, translucent. They're machined on the CNC machine. Then they're put in a CNC milled cradle so we could machine the other side and build the whole thing. This was a heavily digital project. I mean, there were probably no paper drawings on this job at all. There's the LED lighting being installed. There's the halves of the bubbles with the other half yet to be assembled around the steel branches. There's Lawrence. I don't know if anybody have you heard of Lawrence or know him. He was a great sculptor, died at, 47 years old or something. Went in for some procedure at the hospital and never left. But he did a lot of really interesting work over the few years that he worked. He was a professor of sculpture at Denver University. This is kind of testing out the lighting. This is getting it ready to ship. That's shipping, installation, taking off the packaging, which probably was the biggest pain in the neck of the whole job. And there's the piece installed, and there's the piece with lights on, and there's the piece with slightly different colored lights on. So, again, here's where we are today. Here's some of the more experimental projects we're doing with CCA in Los Angeles. I'm getting close to your questions, so get ready. And this is an interesting project because this is a floating building. I mean, one of the most expensive things on a building is the foundation. So why not just get rid of the foundation? I mean, fiberglass works fine in the water. It's been sitting, I mean, boats sit in the water for 50 years and just sit there. So make a house out of fiberglass with the bottom designed to float and forget about the foundation. In fact, forget about the lot. If you get tired of your neighbor, you just pick up the anchor and move. Here's some other composite parts that architects have been experimenting with. That's Zaha's pavilion in the Chanel pavilion. This is a project in South Korea that has gills that open up, these vertical fins open up for ventilation. And this was Knipper Heibig engineers looked and looked and looked for a material that they could flex like this and then tighten up and make it work. The only thing they found was composites. So now he's written a book on composites and architecture. This is a ceiling of an airport in Uruguay by Rafael Viñoly. This is the largest FRP roof I think I've ever seen. There's an all-composite, beautiful, isn't it? This is an all-composite Arctic research facility, designed, of course, by engineers, as you might be able to tell, but very efficient, and notice it's all on skids, so they just tow it to the next place. This is the scariest building in the world. I think it's interesting. It's fascinating attempt at trying to exploit composites. It also exploits the translucency of composites, but it does so at a big price, and that is by not really fully understanding the materials, or maybe even worse, not caring that much. They've built this entire hotel out of a highly combustible material. Translucent FRP burns, and one of the big impediments to using FRP in architecture has been the fire retardants. And we're getting that solved now. But this thing, if you're in this building, my advice would be to stay as close to the ground floor as you can and be ready to move at a moment's notice, because this thing will go up like, I mean, you couldn't design a more combustible facade. Hopefully we don't have to read about that someday. Another opportunity for composites in architecture just down the street. And here, it's close to home, you folks might recognize this. This is Tom Wiscombe's, what he calls his Boneless Chicken. This is a building on top of a building, and because of it, he liked the idea of it being lightweight. And so when I told him, well, let's just build it all out of composites, forget about the steel. So since that day, he's been calling it the Boneless Chicken. And whether it'll actually get done or not, I don't know. But if it is possible to do this at about 1/3 the weight of a conventional building. And then, of course, Peter Testa's tower. I can never resist this slide because it's an example several years ago of an idea about building a building on site out of composites. And the day will come when that happens. And it's already starting to happen in a few places, but this is really looking at the future. But the future is getting closer and closer and closer, and it's your guys' job to make stuff like this happen.